Hello, welcome to another episode of CRIM 7920, Survival Analysis and Longitudinal Data. So in this class, we'll be talking about parametric survival regression. Without further ado, let's just get into it. So what I'm going to do in this class, I'll do a brief review of the Cox proportional hazards model. I'll talk about two different flavors of parametric survival regression models. So, these would be proportional hazards variations and a new accelerated failure time variation. Talk about some of the major distributions that are used with these models, which can be a little bit different, than what we've used so far with the generalized linear model. And finish off with a very brief preview of so-called split population models. Okay, so in the previous class, we had talked about the Cox proportional hazard model as a very popular, in fact, the most popular technique for modeling continuous time survival. So this is where we have very granular time points. We might have many hundreds or thousands of unique time points that, look, we could always bin them into some, discrete discrete categories. We're trying not to be arbitrary here. We're trying to maintain as much information as we can. How do we work with these? The Cox model is the most flexible and popular model for doing that, in part because it makes no assumptions regarding the shape of the baseline hazard function. It takes a lot of the work out of that. However, it does sacrifice, much of what we're looking for when it comes to, well, I want to be able to describe how my my covariates are related to the timing of events. Okay. Okay, there we go. Working with Zoom stuff. So in this class, we're going to talk about parametric survival models. So that is, let's try to make an assumption about what the baseline hazard looks like. And we'll introduce, ways that we can actually describe, how variables influence the survival time directly. So recall, this is the formula for the Cox proportional hazard model. We model the log hazard specifically, which we say is a linear function of some unspecified baseline hazard. That's H sub 0 right here. We assume that this hazard function has some general shape. It can have any shape. It can be flat, it can be curved, it can look like steps, it can write JSON, over time, it can do anything. We just assume that it takes on the same shape for everybody, but it differs in height, up and down the y-axis on the hazard on the basis of these relative ratios, these hazard ratios here, these beta coefficients. Its calculation, in order to essentially assume out the baseline hazard function, it uses semi-parametric likelihood, which essentially asks, so given that a failure time occurred at a particular time, at time J, how do the characteristics of the person failing at that time compare to those who are still at risk? And so again, this is the way that the model tries to compensate for censoring, is that it is not borrowing too much information from censored observations, only comparing them to individuals who do fail, and then using those comparisons to create these hazard ratios. So again, you saw that there were 61,000 citations of this since 1972. So it's pretty easy to find some. So here's one that was looking at, this was a randomized controlled trial that was looking at the application of cognitive behavioral therapy among parolees in Honduras. And so what they were interested in modeling was survival in terms of whether they had received a technical violation on parole. So you're given conditions, don't talk to this person, don't do drugs. They vary depending on who they're applied to and the country. But they're interested in modeling whether they incurred a violation that led to their parole being revoked, being sent back to prison. And so their time metric here is continuous. They have the number of days until revocation or censoring. And you can see down here, they have a pretty small sample, relatively small. Okay, so they've got 100 individuals, 50 in treatment, 50 in control, and these individuals were randomly assigned, to those different conditions. Now, with the number of days that they're following up with here, you could end up with, again, hundreds, if not thousands, of time units. So this becomes very challenging to model in a discrete time case unless we wanted to get we sacrifice a lot of information and get very chunky, with those survival intervals. So just to highlight here the way that they talk about their model, because this is something I see quite a bit. Again, it looks it looks fancy. It looks like something that if a journal is saying, and these journals do exist, you have to include a formula. You have to represent your analysis in terms of an equation. You can present this, and what you realize is that this is just another way of saying that exact formula that I put, on the slide prior. We're simply modeling a hazard function, so the hazard of some, outcome occurring by some time given some covariates, which is a function of a baseline hazard, and then a multiplicative function of those hazard ratios, right? So again, we're not saying a whole lot, other than what we've already covered here in class. But I want to highlight something here. So notice the way that they talk about this. So given that we are interested not only in whether an individual reoffends, but the timing of their new offense, this study will use a Cox proportional hazard model to estimate the causal effect on time to reoffending. At the core of the hazard multivariate models is this question: what are the factors that increase or decrease the time it takes for a failure to occur? In other words, we're interested in not only the shape of the hazard function and survival probabilities, but also the factors that aggravate or mitigate the rate at which events occur. So I want you to think about that for a minute. Maybe pause the video. I'm going to ask you to do that a couple times over the course of this lecture. Is that accurate? Is that a good rationale for utilizing a Cox proportional hazards model? So pause the video, you pull up your phone, find the Jeopardy theme on there, and play that in the background for a minute while I take a sip of coffee. Are you back? Hopefully. So no, that's not the reason. It's not a good reason to use the Cox model. The Cox regression model does not tell us about these things. So recall that how does time factor its way into the hazard ratios that we get from the Cox model? So again, it differs from logic regression in that we're not just looking at the occurrence, the event, right? Not only in whether an individual reoffends, it's true, but the timing of the offense. How does that work its way into the Cox model? It works its way in through the ordering of events only, right? So it is incorporating information about the order in which units fail over time. So who fails sooner, who fails later, who doesn't fail at all. And it's looking at characteristics of those individuals, and it's leveraging that information to produce these time constant hazard ratios. But it's not directly modeling the timing of the new offense. You cannot look at a Cox model coefficient and infer directly that this increases or decreases the survival time. You could, I guess, if it's a strongly positive or strongly negative, you get a little bit of information about that, but by how much? It doesn't tell you, right? So no, that's a terrible reason to do that. But that's what the accelerated failure time models that we'll discuss in this class do. So here is a presentation of their results. So they're presenting the hazards ratio and a 95% confidence interval for that ratio. And so recalling with the interpretation here, so the hazard ratio, we're just exponentiating those log hazard coefficients. It's a multiplicative effect, the unit shift in the covariate on the hazard function. Again, this unspecified baseline log hazard. So think about this. What do these results suggest about the impact or the causal effect of the participation in the cognitive behavioral treatment on the hazard of a parole failure? Pause it, Jeopardy music, think about it. So here, the hazard ratios are multiplicative. So they can only be positive. A hazard ratio above 1 means that it increases, this variable increases the hazard of the outcome, while a hazard ratio below 1 decreases the hazard of the outcome. So in this case, participation in cognitive behavioral therapy decreases the hazard of a technical violation by quite a margin. It multiplies that unspecified log hazard function by 0.34, which is, again, it's about a 76% decrease or so, which is quite large. Now, just as a general point of review, again, might be helpful to think about this, pause the video and think it through for a moment. So notice the modeling strategy here is that they have, well, I guess we would consider a zero order association. So bivariate, just treatment control, on Y. And over here in this model, they incorporate all of these participant level controls. So why is it in this case that the hazard ratio for the cognitive behavioral treatment effect barely changes at all after incorporating all of these predictors into the model? So think about that for a moment. So the reason being, in this case, it's a randomized experiment. All right, so what we did was we randomly assigned the parolees to these different treatment and control groups. The purpose of doing that was to make this, participation in the treatment orthogonal or uncorrelated to any of these other potential competing causes. So if any of these variables differed systematically between the two groups, then we might expect there to be a difference in terms of the hazard ratio predicted here versus over here. Instead, this again is demonstrating that what's beneficial about random assignment is once we've done this, assuming the sample's large enough, you can include any measured, any unmeasured covariate, and it should not change this treatment effect. So again, very powerful design. So an important assumption that is not described here in this table is the proportional hazards assumption, which assumes that this unspecified baseline hazard is the same shape for every subject, and that over the entire survival duration, this hazard ratio can describe the relative distance between the baseline hazards for individuals in the control group and individuals in the treatment group. So again, if you are presenting a Cox proportional hazards model, I strongly encourage you to present some section either in the results or in the kind of analytic strategy in which you discuss the proportional hazards assumption and how you assessed whether or not it's reasonable in this case. In the previous class, we had talked about strategies for working around it if there was a problem, but don't ignore it. So if I'm reviewing and you're presenting a Cox proportional hazards model, I want to know, was the proportional hazard assumption met? How did you determine whether or not it was met? All right. So let's talk about parametric survival models. So part of the ingenuity, of the Cox model is its flexibility. All right. So we are able to get down to, we have our research questions often in survival are not necessarily about the shape of the hazard. It can be. And when it is, you should usually use some kind of discrete time method. But if your question is just about how different variables are associated with the hazard, the Cox model gets around having to explicitly model or even think about the shape of the baseline hazard. which is nice. But, you know, when you think about it, in most other regression applications, we always seem willing to recognize some assumptions about the distribution of the dependent variable or the error term. So for instance, if we have a quantitative variable, we're usually willing to assume that the outcome is going to follow a normal distribution or that its errors will follow a normal distribution. We seem willing to assume that when an outcome is binary, that it's reasonable to model that through some binomial distribution. So again, like these are sometimes they're strong assumptions, sometimes they're weaker assumptions, you know, that can be relaxed, but we're usually willing to make some assumption about the shape of the base of the outcome and its errors. Same thing can be said here about the baseline hazard function. Yes, the Cox model is strong. It allows us to essentially completely ignore the shape of it. But I mean, do we really have to do that? Can't we think about this just a little bit? And again, this draws some of that comparison where, you know, why is it that the Cox model has not been fully implemented in a Bayesian framework to date? And part of that is that, again, the way that you would think about the modeling problem from a Bayesian perspective is you would be willing to make some assumptions, you know, about those distributions. So what's helpful when we do have some distribution that we are going to work with, you know, for the errors, is that this allows us to make predictions. You know, it allows us to you know, based on a new set of data, make predictions about certain sample statistics, you know, means, lower 95% confidence intervals, upper 95% confidence intervals, that sort of thing, for future cases, that sort of stuff. The Cox model is not good at making predictions because, again, it's being completely agnostic about the shape of the baseline hazard. So then it cannot then extrapolate out to say, well, if the survival duration were to continue, what would the hazard look like? And so here it can make predictions within the bounded time frame. So like if the time frame in our study with our Rossi et al. Parolees and rearrest is we have 52 weeks of follow-up. So the Cox model can make predictions within those 52 weeks. But at that point, it hits a wall, right? And that, again, the right censoring, you know, goes off into the distance. It can't make predictions that extrapolate beyond that. But if we had some other distribution that we were working with, then we could make predictions if we wanted. So what parametric survival models do is they fit the hazard according to some known distribution, which allows us to make some assumptions about the shape and behavior of the baseline hazard, describing it through the use of different parameters that are tied to these different distributions. And these parametric survival models have two different flavors that we can use. There are other proportional hazards models, which are interested in describing the hazard function. And so it will produce coefficients which describe how the hazard function increases or decreases, but some specific hazard function. And then there are accelerated failure time models, or AFT models, which directly model the log survival time. And these are really cool. So in general, you know, we have a very similar looking formula. We have the only difference between this and the Cox model is here, H sub 0, our baseline hazard, we assume has some particular shape that can be described by some particular parameters. Otherwise, the covariates are assumed to follow, again, this multiplicative function where those hazards are all assumed to have the same shape for each subject, but some known shape, and they differ in terms of their height, you know, on the y-axis. And so this is a bit closer to how we work with this in a discrete time problem. With accelerated failure time models, notice that we are directly modeling the log survival time. All right, and so we say that the log survival time is a linear function, of different covariates. They can be time varying. They can be categorical, they can be numeric, and some error term, which again is the errors are going to follow some particular distribution. The covariates are assumed to have multiplicative effects on the survival time. So we're going to describe those as like shrinking or expanding the survival time. And you can think about those otherwise as acceleration, where these models get their name, or delay factors on the occurrence of the event. So the primary assumption in these models with this multiplicative effect is that when we take essentially the not hazard ratios, but we'll call AFT ratios, accelerated failure time ratios, is that we have some hazard function, of a particular shape, and that these ratios can be used to describe the stretching or contracting of that, essentially survival time, depending on different characteristics. So, but again, not that the nature of survival, and I'm going to use hazard and survival a little interchangeably, just remember that they are complements to one another. So like larger hazard means lower survival, or like faster shrinking, survival. So we're kind of looking at the complements here. Again, it's assuming that for all subjects, that shape is generally the same, but that we can describe essentially the length or width of the hazard curve on the basis of these exponentiated AFT ratios. So the classic example that's used here, and it's a little misleading, but again, I think it's helpful for understanding, is the dog years example. So when you think, just imagine in your mind, I know in class we talked about what the shape of the hazard for human mortality looks like, where it's initially, it's low, but it's higher than it is at some later point in life. So it's initially a little high, and then it declines. And then as people get older and older, the hazard curve goes up and up and up, and just due to old age, so the likelihood of mortality. So what does the hazard look like for dogs, right? So for dogs, it's not differently shaped, like little puppies, the risk is generally higher than if they make it, if they survive, beyond the first week, for instance, the hazard declines, and then it goes up and up depending on old age. But so the shape is the same. However, let's say in a data set, we had a data set of dogs and people, and we were describing, what's the association between being a human, and hazard, versus being a dog. And we would get this AFT ratio, which should suggest that the human survival time is essentially the same shape as the dogs, but it is stretched out by a factor of 7. So that is, humans survive about 7 times longer, than dogs do. But so again, this is what's misleading, is that, the 7 years, of dog years for every human years is not exactly accurate. It depends a lot on breeds. Some recent research suggests it's a nonlinear function. Whatever, ignore that stuff for right now. But you can understand the premise is that we can have this ratio which describes how that survival is stretching or contracting on the basis of some subject characteristic, in this case being a human versus being a dog, but the shape is still the same. So there are different distributions that are used for performing these types of survival regressions. So the ones that are commonly used here are the exponential distribution, which has both proportional hazards and an accelerated failure time variant to it. These are useful when, the exponential distribution has only one parameter. It has a rate parameter. So this is useful when the hazard is assumed to be constant. Over time, the hazard does not change. I mean, I'm not sure if I could think off the top of my head of different phenomenon that meet that scenario, but I suppose they could exist. So that's the simplest one of these here. The Weibull distribution can be used when the hazard is monotonically increasing or decreasing. So remember that that's just going up or going down over time. It does not have to go down at a constant rate. It can go down at a nonlinear rate, but it is always increasing or always decreasing. So Weibull can do both proportional hazards or accelerated failure time. And because it does that, and because many things demonstrate monotonic hazards, it is a very popular, often default option for parametric survival regression. The Gompertz distribution can only do proportional hazards, and it is useful when hazard functions are highly skewed. So again, when you think about the hazard for humans, it declines, very slowly, and it's essentially flat. And then as people get older, it increases like exponentially, beyond that point. So log normal and log logistic are useful for hazards which increase, or decrease over time to the extent that they switch directions. So these are for, think about nonlinear hazards. And then the generalized gamma is an extension of the Weibull, just adds another parameter. And it is useful for monotonic hazards that need to be wider or more narrow than the Weibull distribution allows for. And speaking of this, one thing I'll highlight here is I will show you what some of these look like in terms of what they assume about hazards. But if you ever look at these distributions and you're just like, whatever, these are just words, he's just throwing words out at me. I always encourage you to try to look these up in software and visualize them. Like, so JASP, is some freeware software that has a great distribution module where you can take a look at what these different distributions look like. So, for instance, here I've got the exponential distribution. It has a rate parameter. You can see how the distribution changes in shape as you update the rate. Let's see, this is working on Zoom, so it might take a second. So you can see that changes, a little bit. So you can explore kind of how that works. Then I've got, Weibull down here, and you can see that when it has a scale and a shape parameter, which again, I'll discuss in a minute. But notice when those are both 1, it is equal to the exponential, distribution. But if I were to change this to, something like 0.5, we can see how that begins to change shape, change this to 2, you can see how it changes shape again. And so again, here's, log normal, log logistic. It also offers some, explanatory text on like, what are its parameters, what are its moments, how does it work? So again, I would always encourage you hear about this, don't just glaze over, look it up, try to understand. So what is this distribution? What are its parameters? What do they represent? And it really helps you understand the situations in which they can be useful. Okay, back here. So most of these distributions, so like exponential only has 1 parameter. It has a rate or a scale parameter. And what these typically do is they'll describe the rate of event occurrence. So how often do people actually experience, or how often do units experience the event of interest? So this can be higher or lower depending on how rare or how frequent the event is. They'll also have a shape parameter. So like Weibull has a scale and a shape, which defines essentially nonlinear change in the hazard over time. So typically when the shape parameter is greater than 1, that suggests that the hazard's increasing. When it's less than 1, it suggests the hazard decreases over time. So, all of these different distributions have both scale and shape parameters, but they have, in terms of their probability density functions, they have different formulas, for how those parameters relate to the probability of the outcome. So in terms of implementing these, there are 2 major packages that can implement these types of models. So in survival, there is a servreg function, which works just like CoxPH, but it allows you to specify a dist argument. So here we can see, it takes a survival object as the, survival object as the dependent variable. And then the distribution we specify as Weibull. And then you can see when you pull up the help file for this that which distributions are allowed and what do they do. The servreg function only supports a small number of parametric distributions. There is a different package. So the flex serv package has a flex servreg, which is more flexible. And so it has a very similar setup. And so these will both be kind of equivalent, but we'll see that it also has, I believe the default here is that it does a Weibull accelerated failure time. We have different arguments we'd specify if we wanted the proportional hazards variant, for instance. So for instance, so I'm going to use flex servreg for these examples. So looking at what how these distributions shake out in terms of the hazard here. So notice what I'm doing is, and this is part of the exercise of what we do. So think about this like going back to regression analysis, where, big modeling question is, what is the likelihood? All right, so what likelihood should I use to describe the probability of the data? So that's what we're doing here. What I would recommend is you create a survival object, and then we're doing an unconditional. So we're just estimating an intercept, and then we are testing different distributions. And so I'm fitting this, and then this is the fitted hazard that comes from that. It predicts a flat hazard right here. Then what we're going to do is engage in multi-model inference to ask, even without the covariates being factored in here, which of these distributions is most likely to have produced the data? All right, so that's essentially what we're doing. So here, exponential describes flat hazards because it only has that one scale parameter or rate. So Weibull distribution is, the hazards allowed to monotonically increase or decrease. So here, this is that estimated hazard, again, applied to our data. So it is assuming, again, the model provides a framework, for predictions to be made. And so it says, all right, so I've got a distribution here, which allows the hazard to monotonically increase or decrease. Based on what I'm seeing in the data here are the estimated parameters, that I can produce that provide the best fit, for the toolkit that I have, right? So the underlying question is, how well does this fit the actual hazard function? So we'll get to that in a minute, but this is the Weibull's attempt at describing that. Note the default here. So we just say dist equals Weibull is it's doing the accelerated failure time. If you wanted the proportional hazards variant, and a little bit more on that later, as we go, you would set Weibull pH, to get that. So here's log logistic. And so this allows more nonlinearity in the hazard. So it does not have to be monotonic. If you carry this out over time, so again, let's say we extended out the time frame, Weibull is always going to remain positive. It's never going to shift negative. Log logistic will at some point. It allows for that possibility to happen. And so this is done with the L logis. So this is all of those different distributions mapped out. So you can see some of these other ones. So like here's the Gompertz, the gold is the generalized gamma. And again, that's related to Weibull. So you can see it's producing very similar predictions to Weibull here as well, as is the log logistic in that case. So what you would do if you want to figure out, well, I don't know, which one of these should I use, to describe the hazard in this case? We use multi-model inference. So this is a great article. So Hamilton and Campbell, they looked at, and all these examples have to do with parole failure and that kind of thing, but it's a great place to utilize these methods. we can see as all these different types of outcomes, any return to prison when they had a halfway house violation, et cetera, and then is estimating null models, like these here, and comparing. These are the AICs on each of them, and you can see in almost every case for his data, the log normal model. So this assumes that the hazard or the survival times follow a log normal distribution. That appears to be the best fit in every case, with the exception of the new commitments, which follow a Gompertz distribution. I think because in this sort of scenario where he's got these multiple outcomes, because most of them fit log normal, he just applies that to everything. That's reasonable. In this case, I think it would also be reasonable if you just had note this last model uses a Gompertz likelihood. I think that would also be fine. So in our case, we've got our AICs, we've got our BICs. So which one of these provides the best fit to the data? Take a look, think about it. So what you can see is that the lowest AIC and the lowest BIC is the Weibull distribution. So again, a monotonically increasing hazard. It's very, very close to the log logistic likelihood here as well. So in this case, you could probably do a little bit more research on what's the difference between the Weibull and the log logistic distributions and the scenarios in which they are useful. It's a great question to ask ChatGPT. For instance, Weibull, because of its popularity, because it's often a default option and it is a bit more parsimonious than a log logistic, we're going to go with that for continuing our analysis. So we're going to use a Weibull distribution. And so what we essentially have to compare this back to is, remember what these are trying to do is they're trying to capture the hazard in this continuous time case. That is a very difficult thing to represent, right? So these are always going to be an approximation of that. When we look at this smooth hazard, we can see that, as it kind of smooths out right here, it does appear to have a bend in it, like at one point, but it is generally increasing over time. This could be why both the Weibull and the log logistic appear to be good fits to the data. So I'm going to go again with the more parsimonious one and use the Weibull distribution. So here you can see I've used FlexServReg. This is on my rearrest survival object. And the distribution is Weibull, and it's Weibull meaning AFT, so accelerated failure. So note one thing that this summary does that can be a little confusing sometimes is it does provide the mean of the data here too. So again, this is a RCT, so 50% of the sample were in the financial support group and 50% were not. That's why this is 0.5, right? So that's the data. Here are the parameter estimates and their confidence intervals. So when you see these, the NAs, sometimes oh shoot, did I do something wrong? No, it's just that's the data mean, and these are parameters. The parameters are not data unless you're in a Bayesian sense. These don't have data means here. So first, we do get the estimates for the scale and the shape parameters. So because the shape is greater than 1, that suggests the hazard is increasing over time. Again, makes sense. It's what we saw. And the scale defines the width of the hazard function. Just you can think about it in terms of how quickly it's accelerating or decelerating. And then we can recover, 1 divided by the scale gives us that estimated rate from an exponential distribution. So here we have our accelerated failure time coefficients. Now these are going to have, what can be confusing here is that these are describing the impact of the covariate on the log survival time, which is not the same as describing the impact of the covariate on the log hazard function. So they're often going to be in different directions than what you would get with a proportional hazards analysis. So here, positive coefficients mean that a unit increase in that predictor increases the survival time before the event occurs. All right. So a positive value means that a unit increase means it takes longer for the event to occur. All right. So it increases survival. While a negative one decreases the survival time, means events happen faster. So here, the financial support coefficient is 0.27, right? So if we were to exponentiate that, we get this acceleration factor, which is 1.313. So what that suggests is being on financial support compared to the control group stretches the survival time by about 31%. Which again, that's cool, right? We are directly describing the association between the predictor, the variable we're interested in, and the survival time. All right, so that's a very appealing feature of these models. So again, don't be fooled, by analyses using the Cox model, which suggest, hey, well, we're really interested in time until event occurrence, so we are using Cox. Like, use Cox when you want to incorporate information about the ordering of events. But if you are directly interested in modeling the impact of the covariate on how long before an event occurs, this analysis does that, right? Cox does not do that. So I encourage you to pause this, take some time to look at these coefficients. And again, there's no p-values here, but if the confidence interval crosses 0, that tells you that the effect is not statistically significant. We've failed to reject the null. So you can take a look at some of these and kind of try to interpret what the results imply. So as I'd said, accelerated failure times are modeling the log survival duration. All right, while proportional hazards are modeling the hazard function. So they have opposite signs because of that. So here, these are the same model, but I estimated with the proportional hazards variant. And so you can see that the financial support coefficient for the proportional hazards model is negative, right? Which is very similar to what we saw at the Cox model. It's very similar in scale as well, that it suggests that being on financial support compared to the control group decreases the hazard, right? Which subsequently increases the survival time. It stretches the survival time, right? So it makes sense that these would be opposite signs. So just keep that in mind when interpreting these results. So one helpful feature, again, of these models is they enable you to make sensible predictions about hazard, about survival, and we can even take it here. I'm just taking it up to the 52-week marker, but we could take it further than that, for instance. So if you go into the script, one thing that I do is using the Weibull model, I essentially ask it, so what do we, based on this model, what do we predict the average survival time is? And remember that this is something that we could not estimate just in terms of, I know how long they survive, give me the mean, because of censoring, because when people don't experience the outcome, their true survival time is unknown. Well, in this case, we can make the assumption about the survival times following a Weibull distribution. And doing that allows us to say that we expect about 50% of the sample to eventually fail by 136 weeks. And so that makes sense. When you look at this, you can see how the survival is essentially flattening here over time. This would have to extend out on the x-axis, but until 136 weeks. Again, that's in the treatment group compared to the control group, for 104, which again, when you look at those coefficients, the difference, the ratio between those two, my wife's trying to be quiet as she goes up the stairs. When you look at the ratio between the two, that equals out to that accelerated failure time ratio of about 1.313. Okay, so taking a look at an example of these applied in research. So common application of survival analysis is looking at the timing until some first event. So in this case, we'll call the timing of sexual debut. And so this is what age, so individuals among African, Caribbean, and Black men in Canada, how long until their first sexual intercourse. So the event here, is that age at the first penetrative sex, and then the time metric that they're using is years. Now, again, that's a relatively thick. They do have a very large number of years that they're considering, again, from teenagers up until 80, 90 plus, right? So here's a nice description of how they decided how to use these accelerated failure time models. So what I'll just highlight here is they say, so to establish, the model of best fit, we examine the distribution of the dependent variable, which is age at first sex, and was observed to be approximately normally distributed. So because of that, they believe that the log normal survival, would be appropriate. And so this is kind of what they expect that survival, the distribution of survival times to look like. What they then do, that again, that's their assumption about what it would look like, is they then compared them according to information criterias. And so the different accelerated failure time models indicated the log normal model as the best fit in returning the lowest AIC value. So again, this is just a nice setup to how you would justify the approach. So again, I have this outcome, I examine the survival times, I think about what that would look like, I know what these different distributions can accomplish, and then I compute all these different models just using the intercept, and then use multi-model inference to figure out which distribution is most appropriate. So here are some of their results. So again, these are accelerated failure time ratios. So they call these time ratios. I don't know if that's just something you do in that field. But recall, these are multiplicative effects on the survival time. So recall that an AFT ratio greater than 1 means it stretches the survival time. And if it's less than 1, it shrinks the survival time. So again, you might want to pause this and take a look at a few of these different parameters and see what you could do about interpreting these. What do they suggest? So here, like using, so they have 50 plus year old, as the reference category. So among individuals who are 15 to 19, assuming that they haven't experienced sex yet, right? The timing of their first sexual intercourse, it takes about, it's 0.815 times the survival time for those who were 50 plus and had not yet experienced sex, which is about a 20% decrease or so. However, you could look at some of these other variables here. So if an individual is Muslim, compared to other for religion, I don't know why you'd use other as the reference category. I think that's not very wise, but it suggests that individuals who identify as Muslim, that stretches the survival time by 1.2 times compared to those who are other, which again, if you want to make some assumptions about, what that means for, faith and following faith, suppose that makes sense. Okay, so finally, let's talk about what's called the split population model. So this is where you can think about this as kind of being like a hurdle model for parametric survival time. So far, we've assumed that whether we've done Cox or whether we've done parametric, there's some underlying baseline hazard function, and that applies equally to all individuals, but it shifts, depending on, like, just in height, depending on their covariates. But it does assume that for whatever the outcome is, at any point there is some hazard. For me, right now there is some hazard of mortality. Hopefully it's low, but it's there, right? What researchers that kind of forward these models indicate is, like, I don't know if we should really assume that that underlying hazard is the same for everybody. There's probably some units, in your data that might not be at risk of the outcome at all, right? So again, like a classic example on this would be developing lung cancer. All right. So we're following individuals looking to see if they develop lung cancer, and you have people who smoke and people who don't. The people who don't smoke are going to be pretty low, on that, right? So like we really assume that there's some general hazard that is affecting them as well. So what a split population model tries to do, and I encourage you to look at this link because they describe the methods pretty nicely. So it works like a hurdle model. We're actually going to use two different models, logistic regression to describe the probability of event occurrence, and then a parametric survival model to describe what they call the duration or the time at risk. So these models are, I'd say, relatively new. At least I don't see them used super often in criminology. So this was a paper that came out probably 7 years ago or so. And the main kind of story behind this paper is simply like, hey, maybe the hazard of, a new crime, we can't assume that there's some general hazard that affects everybody. So it's just a very general, like, do split population models work here? And this is published in the top journal, in CRIM. So it was, assumed at least a few years ago to be a very unique application. So you can look at some of the text here. So, what they're initially looking at is like the simplest parametric model, assumes that the time between sentence and recidivism follows an exponential distribution or a time constant hazard rate. But our examination of hazard rates suggests this probably isn't the case, right? So they highlight this split population modification, which again was so Maltz and McCleary, older criminologists. You might remember McCleary from the autoregressive integrated moving average models. So he's very active with this stuff after completing his dissertation. So they know how to do it. It's just not applicable in software yet. Now it is. So this model makes two key assumptions about recidivism and desistance. There's a group of offenders who have already permanently desisted at the time of them receiving their sentence from prison. They're just not going to commit another crime. This would be especially true for individuals who are older, for instance, and then others who are still active and they have some time constant exponential recidivism rate. So, what they do in their analysis is they essentially compare different parametric distributions, so exponential, Weibull, log normal, and compare them to their split population variance. So split population exponential, split population Weibull, and then are comparing them, on the basis of these different criterion, right? And so essentially what they're highlighting here is that the it doesn't actually look like the split ones work super well in this case, but like they're investigating whether or not they're useful. So the way that we can estimate these models in our data is we use the SP duration package. So this package can only do Weibull or log logistic. So again, you can think about this as monotonically increasing or decreasing, or kind of a non-linear expansion of the Weibull distributions. Remember that these two fit our rearrest data pretty well. And what it requires is your data to be converted into long form first. So it can create a relatively large data problem. So check out the script for an example of how that was done in this case. I know I talked about it in the last class, but we use the spdur function, so split population duration. We have two different things that are done. So duration is automatically fixed, like that's just the time here. And then arrest is the event, right? And so we have the same linear function for each of those, and then we use a Weibull, for the duration model. So here we, just like the hurdle models, we get two different sets of results. We get a duration equation, we get a risk equation. So risk is on the basis of logistic regression. So here, positive coefficients mean an increased likelihood of the event. Negative coefficients mean decreased likelihood of the event, and it doesn't appear to be a lot of action going on here. But here in the accelerated, the duration equation, these are AFT ratios. So positive means that it increases survival time. Negative means it decreases survival time. So it happens more quickly. So for instance, if an individual has work experience, this vastly expands the survival time. So people with work experience survive significantly longer before experiencing rearrest. It's a close, but it does not appear that financial support gets that done in this case. The more prior convictions that you have, the shorter it shrinks the survival time. And again, you can exponentiate those to get the specific ratio for that. That's it. So next time, we're going to talk about some expansions of the Cox model. So looking at what if I have many different kinds of events? And then what if I have some kind of dependence or repeated measures? How does survival analysis and the Cox model deal with those? So looking forward to talking about it then.